Welcome back to Bite-Sized Breakthroughs. Today we're diving into a paper that shakes up the world of deep learning optimization, specifically in the realm of network pruning. Joining me is Dr. Paige Turner, the lead researcher on this fascinating study. Paige, thank you for being here.
It's great to be here, Alex. I'm excited to discuss this work. It challenges some long held assumptions about network pruning, and the implications are quite significant.
Before we get into the specifics, let's set the stage for our listeners. Could you explain network pruning for those unfamiliar with the term?
Certainly. Imagine a deep neural network, which is essentially a complex system of interconnected nodes, like a vast network of interconnected neurons. These networks are often overparameterized, meaning they have more parameters or weights than necessary for the task at hand. Network pruning is a technique used to reduce the complexity of these models by removing redundant or less important connections or weights from the network.
So in essence, you're making a large model more efficient by trimming away unnecessary parts.
Exactly. This leads to several advantages such as faster inference times, reduced memory usage, and lower computational costs. This is especially beneficial in resource-constrained settings, like mobile devices or embedded systems.
That makes sense. So what's the traditional approach to network pruning, and what are the assumptions behind it?
The typical three-stage approach involves first training a large, overparameterized model. Then, using a specific pruning criterion, you identify and remove redundant weights. Finally, you fine-tune the pruned model to regain any lost accuracy. This approach is based on the belief that a larger model provides a better starting point for pruning and that the inherited weights from the large model are crucial for maintaining performance.
Interesting. So your paper challenges those assumptions head on?
Exactly. We discovered that for structured pruning methods, which prune at the level of convolution channels or even larger, fine-tuning the pruned model often yields comparable or even worse performance than training a smaller model from scratch without inheriting any weights.
Whoa, that's a pretty bold claim. What exactly are structured pruning methods, and how do they differ from unstructured methods?
Great question. Structured pruning methods remove entire groups of weights, like entire channels or layers, preserving the overall structure of the network. This is in contrast to unstructured pruning, which removes individual weights scattered throughout the network, leaving a sparse weight matrix.
So, structured pruning keeps things organized, while unstructured pruning can create a more chaotic, sparse network.
That's a good way to put it. Structured pruning is easier to implement and more efficient in terms of memory usage and computational cost because you don't need specialized libraries or hardware to handle sparse matrices. It's more compatible with traditional deep learning frameworks.
That's helpful. Let's dive deeper into the specifics of your methodology. You mentioned training from scratch. What does that entail, and how is it different from fine-tuning?
Training from scratch means starting with a randomly initialized, smaller network based on the pruned architecture and training it directly on the target task. You're essentially bypassing the large model and its inherited weights. Fine tuning, on the other hand, starts with the pruned model but initializes its weights with values taken from the large model. Then, you optimize these inherited weights further to improve accuracy.
So it's like starting a new model from scratch, whereas fine-tuning is like tweaking an existing model to adjust its performance.
Exactly. And our research suggests that in many cases, especially for structured pruning, training from scratch can achieve comparable or even better results than fine tuning.
This is really fascinating. Let's talk about the experiments you conducted. Which pruning algorithms did you examine?
We evaluated several state of the art structured pruning algorithms, including L1 norm based filter pruning, ThigNet, regression based feature reconstruction, network slimming, and sparse structure selection. We also looked at a common unstructured pruning method, magnitude based pruning. We tested these algorithms on different datasets such as CFAR10, CFAR100, and ImageNet, using various network architectures like VGG, ResNet, and DenseNet.
That's a comprehensive set of experiments. What were the key findings?
Our results consistently demonstrated that models trained from scratch often achieved comparable or even better performance than fine-tuned models, especially for structured pruning methods. This was particularly noticeable on larger data sets, like ImageNet, where models trained from scratch consistently outperformed fine-tuned models. We also found that for many structured pruning methods, the pruned architecture itself, rather than the inherited weights, was more crucial for achieving efficiency.
Can you provide some concrete examples of the performance differences you observed?
Absolutely. For example, with L1 norm-based filter pruning, we observed that on ImageNet, ResNet34 models trained from scratch achieved a top 1 accuracy of 73.03%, compared to 72.56% for the fine-tuned model, a noticeable improvement. Similarly, with network slimming, we found that on CFAR10, a pre-ResNet 164 model trained from scratch achieved an accuracy of 94.90%, slightly better than the fine-tuned model's 94.77%.
It sounds like the performance difference is not huge, but it's consistent across multiple experiments. Did you observe any situations where fine-tuning was superior?
That's a great point. We did find that for unstructured pruning, which prunes individual weights, fine-tuning sometimes outperformed training from scratch, especially on larger datasets like ImageNet. This could be because unstructured pruning significantly changes the weight distribution of the network, making it more challenging to train from scratch effectively on larger, more complex datasets. However, we still observed that training from scratch often achieved comparable performance on smaller datasets, like CFAR10, even for unstructured pruning.
That's a crucial distinction. It seems that structured pruning offers a more robust approach for training from scratch. Can you explain what you found regarding the value of the pruned architecture itself?
Yes, we looked at the parameter efficiency of architectures obtained by automatic pruning methods, where the pruning algorithm itself determines the final structure. We compared these architectures to ones where we uniformly pruned the same percentage of channels or weights across the network. The results were quite revealing. We found that architectures obtained by automatic pruning were significantly more parameter efficient, meaning they could achieve the same level of accuracy using far fewer parameters. For example, with network slimming on CFAR10 using a VG16 network, we found that the automatically pruned architecture could achieve the same accuracy as a uniformly pruned architecture with 5 times fewer parameters.
So automatic pruning is not just about removing weights, it's also about finding more efficient network structures.
Exactly. It's like an implicit architecture search, where the pruning algorithm helps identify the most efficient network structure for the task. We also observed consistent patterns in the sparsity or distribution of pruned weights across different architectures and datasets. This suggests that these patterns could potentially guide the design of more efficient network architectures, reducing the need to train large models and prune them. We even found that these sparsity patterns could sometimes be transferred to different network variants and datasets, demonstrating their generalizability. However, we also observed cases where the architectures obtained by automatic pruning were not significantly more efficient than uniformly pruned ones, suggesting that this approach might not always yield optimal results. It's crucial to carefully evaluate the pruned architecture against uniformly pruned baselines to assess its true value.
It sounds like there's still a lot to explore in terms of architecture search. I'm curious about your comparison with the lottery ticket hypothesis, which suggests that certain connections within a large network, along with their initial weights, play a crucial role in training. What did your findings reveal about this hypothesis?
That's a great point, Alex. The lottery ticket hypothesis focuses on unstructured pruning and suggests that the original initialization of a subnetwork within a large model is crucial for achieving good performance. Our research found that this hypothesis doesn't consistently hold with optimal learning rates, particularly for structured pruning methods and larger networks. We discovered that with optimal learning rates, using the original initialization, or winning ticket, did not consistently outperform training with randomly reinitialized weights. The difference in learning rates seemed to be a key factor in the observed behavior. We found that the winning ticket initialization only provided an advantage over random initialization with a small initial learning rate, but this smaller learning rate yielded inferior accuracy compared to the more widely used larger learning rate.
So it sounds like the initial weights might not be as critical as previously thought, especially when using optimal learning rates.
That's a key takeaway. Optimal learning rates seem to allow for more flexibility, and the focus shifts towards finding the right architecture rather than relying on specific initial weights.
We've covered a lot of ground, Paige. Before we move on to broader implications, I'd like to bring in Professor Weed Spectrum, a leading expert in the field, to provide some additional insights. Professor Spectrum, thank you for joining us.
It's a pleasure to be here, Alex. Paige, your work is truly groundbreaking. It's refreshing to see researchers challenging long held assumptions and pushing the boundaries of deep learning optimization.
Thank you, Professor Spectrum. We're excited about the potential of this research.
I'm particularly intrigued by your findings on automatic pruning as a form of architecture search. This resonates with recent work on automated neural architecture search, but your approach offers a more streamlined, efficient method, requiring only a single training pass. Of course, the search space is limited to subnetworks within a large model, whereas traditional architecture search methods can explore a wider range of possibilities. Still, it's a very promising avenue to explore, potentially leading to the development of more efficient and scalable architectures.
I agree, Professor Spectrum. It's an exciting area of research. We're also looking at the potential for transferring sparsity patterns across different datasets and models, which could further streamline the design process.
That's quite intriguing. And your findings on the lottery ticket hypothesis are also very thought-provoking. It seems to suggest that with optimal learning rates, the focus should be more on the architecture itself rather than specific initial weights. This aligns with the broader trend in deep learning towards more robust, generalizable models.
Absolutely, Professor Spectrum. It's a reminder that there's still much we don't know about the inner workings of deep learning models, and that optimization strategies are constantly evolving.
Paige, let's address some potential listener questions. One might ask, why are these findings so significant? What are the broader implications of this research?
These findings have significant implications for both theoretical understanding and practical applications of network pruning. First, they encourage researchers to focus on more careful and rigorous baseline evaluations, particularly exploring the effectiveness of training pruned models from scratch. This shift in focus could lead to the development of more efficient and accurate pruning techniques. Second, the research highlights the potential of automatic pruning as an efficient architecture search method, which could revolutionize the design and optimization of deep learning models. Third, the paper emphasizes the importance of carefully considering hyperparameter tuning, particularly learning rates, in network pruning and related areas like the lottery ticket hypothesis. Understanding these factors is crucial for maximizing the efficiency and accuracy of pruned models. Ultimately, this research has the potential to lead to the development of more efficient and scalable deep learning models, addressing the challenges of resource constraints and accelerating the development of powerful AI systems.
That's a great summary, Paige. Professor Spectrum, could you add some insights on the potential applications of this research?
Certainly. This research has the potential to revolutionize the development of deep learning models for resource-constrained settings. Imagine more powerful and efficient AI models running smoothly on mobile devices, embedded systems, and edge computing platforms. The findings could also be applied to a wide range of applications, including image recognition, natural language processing, machine translation, and more. This could lead to more accessible and powerful AI systems, driving progress in various fields.
That's a powerful vision, Professor Spectrum. Paige, are there any limitations or caveats to this research that our listeners should be aware of?
Of course. Our study primarily focuses on structured pruning methods, and the findings might not generalize directly to all unstructured pruning techniques. We also primarily evaluate on image classification tasks, and further research is needed to explore the implications for other deep learning tasks. While we compare performance with uniform pruning baselines, we don't explore other architectural design strategies or search methods, limiting the scope of the architecture search paradigm. Additionally, Our research relies on existing pruning algorithms and doesn't introduce novel methods, focusing on reevaluating their effectiveness under different training strategies. Finally, our transfer learning experiment focuses on a specific object detection framework and might not be representative of other transfer learning scenarios.
Those are important points to consider. Professor Spectrum, what are some potential future directions for research in this area?
We need to explore the applicability of these findings to a wider range of pruning techniques, including unstructured methods and techniques for other deep learning tasks, such as natural language processing. Developing more sophisticated architecture search methods that leverage insights from automatic pruning techniques to explore a broader search space is also essential. Investigating the interplay between learning rates, training budgets, and pruning strategies is crucial, particularly in the context of the lottery ticket hypothesis and other areas where initial weights are crucial. Developing novel pruning algorithms that specifically target architecture search is also an exciting avenue. Finally, exploring how pruning techniques can be incorporated into more complex deep learning frameworks, such as those involving attention mechanisms, graph neural networks, and generative models, will be crucial for advancing the field.
It sounds like there's a lot of exciting research to be done in the future. Paige, what are your key takeaways from this research?
Our findings suggest that the focus in network pruning should shift from weight selection to architecture search. Training pruned models from scratch is often as effective or even better than fine-tuning, especially for structured pruning methods. Automatic pruning can be viewed as an efficient architecture search paradigm, identifying efficient structures rather than simply selecting important weights. We need to carefully evaluate pruning methods against uniformly pruned baselines and acknowledge the critical role of learning rates in optimizing pruned models. This research holds great potential for advancing the field of deep learning optimization, leading to more efficient and scalable AI systems for a wide range of applications.
Thank you both for this insightful discussion. It's clear that network pruning is a vibrant and evolving field, and your research is pushing the boundaries of what's possible. We look forward to seeing how these findings shape the future of deep learning. Until next time, this has been Bite-Sized Breakthroughs.